Good morning, Principal Sir, Professor, colleagues from Satyug Darshan Institute of Engineering and Technology, participants from different colleges, faculty members, students, and industry persons. I welcome you all again for today's session, second day of on advances in welcome once again. Our today's topic is turbo machines to harvest marine energy. The main aim of today's learning is how we can run the turbine using the ocean energies, wave generated in the oceans, so that marine energy can be used to run the turbo machines. Today's resource person is Professor Abdus Samad. He has done his BTech and MTech from Aligarh Muslim University and PhD from Inha University, Korea. He worked with the University of Aberdeen, United Kingdom, and Z-Lift Limited, UK, to design novel downhole pumps during his postdoctoral work. He has joined IIT Madras as an assistant professor in 2010, and currently he is working as professor at IIT Madras. He has supervised 8 PhDs and more than 30 MTech and MS students and various BTech projects. He has taught various courses in undergraduate and postgraduate levels like offshore oil and gas production system, well completion and testing, petroleum engineering, marine engineering, ocean mining, computer-aided ship design and drafting, and many more. He has more than 100 publications in various international journals. He has organized around 20 faculty development programs, conferences, workshops at IIT Madras. He has delivered around 30 invited lectures and keynote lectures at various organizations in India and abroad. I hope that today's session will be very enlightening and motivational for all of us. Now I will like to request Principal Sir to welcome our audience and I welcome our resource person. Principal Sir, please.
Morning all of you. And
good morning.
I would like to welcome all of you, the researchers, industry personnel, and faculty members here. And this ongoing 5-day FDP, this is our second day. And we have our esteemed Professor Abdus Samad. And I would like to welcome him. I would like to tell about him. My experience is that actually I was trying to contact him, and in this lockdown scenario, it was very difficult because the offices are closed. It's all work from home for all of us. Somehow I managed to get the phone number of his student, so I messaged him. And I was surprised to get a call directly from Professor, and I was humbled and overwhelmed by his humility, and I respect him, and I really he agreed. So I feel indebted to him that he agreed to give this webinar, and because he is one of those stalwarts in the area of ocean energy. We all know energy is one of the very important topics, and everyone is trying to tap energy from wherever possible. We on the territory almost forget about the oceans, and these oceans, they have a wonder world. One of the wonder is that they have energy in them. The tidal and the wave energies, they can be tapped. My father was also from the hydraulics background, so I learned from him that dikes were being made to store the water during the high tides, and the turbines were used, then specific turbines, because it was a low head situation. So the bulb turbines were being used. They are basically axial flow turbines, very efficient ones. So I will not take much time. Professor Abdus Samad is an expert in this area. Will be throwing all details and will enlighten us. And I'm sure that it will be a great learning experience. I welcome Professor Samad. I welcome you, sir. And over to Professor Samad.
Sir,
Yeah.
before that, I want to announce something, sir.
Yes, yes.
Excuse me, sir.
Yeah.
Dear participants, we will take the question answer session in the last after the session of Professor Samad will be over, and you can raise your hand or you can write your questions in the chat box also, and we will deliver that question to Professor Samad. And if there are so many questions, then we will take your questions through mail. You can send us the mail, or you can send the mail to Professor Samad. He will directly answer your questions. And at the end, in the chat box itself, we will send a feedback form. So you are requested to fill the feedback form at the end, sir. Thank you, Professor Samad. You can now start. Sorry for interruption.
Uh, yeah. Thank you very much for this introduction and giving me opportunity to talk on this turbines for marine energy. This, yeah. So I think there are 123 participants. I mean, they are from all over India. I think so.
Yes, sir.
Yeah. Okay. Yeah, so I'll be taking like say 1 hour for presentation and approximately half an hour for question or discussion things, and I have 56 slides. So sometime I'll go fast, sometime I'll go slow, sometime I'll tell story, and I'll try to explain as much as possible. I have made some paper-based model and some my son's broken toys also just to explain the things. Okay, so. Then renewable energy, again I'll go down to marine energy to wave energy, oscillating water column, buzz turbine, innovation, experiment. So lastly I will reach to my lab. So general global renewable energy overview, India and world, and what is the performance in renewable systems and how we are working, and where is the position for marine energy, and how this where is wave energy within marine energy, because marine energy means it may have tidal energy or desalination, uh, ocean thermal energy based energy conversion systems, or salinity gradient system, or many other types are there. Then among these, wave energy is there. Then wave energy also having maybe 1,000 new different concepts. So among those 1,000 concepts, oscillating water column on device. Again, oscillating water column is having different configuration and designs, and they uses turbine. Then I will enter into the turbine. So 50% time I'll be investing till oscillating water column. Then 50% time I'll go to wells turbine, innovation, safety, optimization, and experiments. Okay, let's see what other things are there. Yeah, India's electricity production position, if you see, we are in third or fourth position actually. I got from Google search, BP Statistical Review, it is showing India is third position in production, but we have limited resources, especially oil and gas. Oil and gas we are importing maximum part. Small part we have, for example, we have Cambay Basin and other areas where we produce. Mumbai High is there, and Assam area is there, Rajasthan area is there. So many areas there for oil production, but still we have limited area or limited reserve. And if you have to produce more, then we have to explore more. So that is not so much easy task, and we cannot do immediately or within one day. So we have to import. And what is the scenario? Little bit I'll discuss on that also, because I'm teaching oil and gas, because I was working in the UK for 2 years for oil and gas industry. And I joined IIT Madras because they started MTech in petroleum engineering, and I was hired to teach petroleum engineering. Also, then later I shifted to marine energy area. So I'll give some overview of oil industry also. So how we are moving from oil to renewable sources. So if you see consumption wise, India's consumption increasing. Why increasing? Population increasing. Say 100 crore to 140 crore almost now. And but production's line, if you see, annotation I have to show here. This production line, if you see, this is horizontal, almost horizontal line. But consumption line, you see, is almost going up. Okay, the sloping. but production is slope almost zero. So we have limited production or no change in production. For example, Bombay High, we cannot change their production rate. Even they are declining actually. If you see Assam area or Rajasthan area or other oil industry, oil producing areas, they are not adding too much oil or gas into our consumption basket. But in consumption area, our economical level increasing, so we need more air conditioner, more electricity consumption, more car, more transportation. So our consumption of electricity increasing or power consumption increasing. So we are getting this gap, joining gap. Okay, so big gap, it is increasing. There is no chance to reduce it now immediately. So then what is the solution? Oil and gas, still people are discovering. You will find regularly in the newspaper that, okay, one field got discovered and this. But discovery does not mean that this will reduce this earning gap. They will add maybe some small amount. So that will not be a huge amount. Okay. So we have to move away, or we have to look at other options. For example, nuclear options. Nuclear, but still you have question whether nuclear you can use safely. You know Chernobyl accident case, or you know Sendai Island few years back, by around 10 years back in Sendai, Japan, there was tsunami, and there was very huge problem of nuclear power plant in that area. So there are restriction of using nuclear power plant. Even France and other country, they have already huge amount of nuclear sources, but they don't want to increase further. So people are focusing more on renewable based energy. I have to close the annotation part. Yeah. So what are the different renewable sources? Renewable sources doesn't mean only the solar energy or wind energy. We have many other sources. Notate, just clear all drawings. Okay. Yeah. So if you see solar energy, it is very much growing in India. India, say, a country which are having lots of sunlight, like African countries or Indian subcontinent or these tropical countries, they're having lots of sunlight. So they can use solar energy. So in terms of PV cell, or maybe they can use solar heating, like simple heating water. But I was working in the Scotland for 2 years. There, almost more than 6 months, I never have seen any sunlight. Winter season, daytime will be around 6 hours, and nighttime will be more than let's say 18 hours. And summertime, daytime will be 18 hours, nighttime will be 6 hours. But daytime, that 18 hours, the sunlight, the intensity will be very low, and there will be cloudy environment, so you do not get actually sunlight. So if you are thinking to put solar energy based system in Scotland or northern hemisphere, anywhere, I mean that nearby North Pole area, so it is not possible. It's only possible where sunlight is strong. Another is biomass energy. Biomass means wood or anything you burn and you get energy, or you digest, you use a digester, let's say gobar gas or any other thing, then you get energy. Another is wind energy. Wind energy also is growing in India, and it is also possible in colder countries also. Hydro energy, especially small hydro energy is there, especially in northern, especially in nearby Himalaya area. Another is geothermal energy. Geothermal energy in India options are there, but still not very much popular or not much explored properly. Another is marine energy systems. So marine energy system I'll discuss. First I'll close the annotate, then I'll go back. Annotate, here drawing. Yeah. So in India, marine energy government has targeted 175 gigawatt of renewable energy by 2020. It will be almost half of the country's requirement. And 100 gigawatt government is expecting from solar, 60 gigawatt from wind, and 10 gigawatt from biomass, 5 gigawatt from small hydropower project like Himalayan area or northeast area. Lots of small waterfall will be there, so government can or people can use energy from there. And India presently installed capacity 84 gigawatt. and it is increasing gradually. And I got this information from Economic Times. Even Ministry of Renewable Energy website also it will be available. Now question is that where is the marine energy in this list? Okay, so in this whole presentation I'll try to explain and justify why marine energy is not in the list and what to do for that. Yeah. Yeah, so in this picture, you see background. Actually, our Department of Ocean Engineering Laboratory is called wave basin. We can create artificial wave instead of going into ocean. We can create wave, and we can test our ships or offshore platforms or ocean energy systems. Anything, whatever machinery or structure it is there in the ocean, we can create small model and we can test it. So if you visit Chennai, maybe you can try to visit our IIT Madras also see this big wave tank. It was developed almost 50 years back. So why do we need marine energy? So world population presently 7.7 billion and 9.7 or more it will be by 2050. Yeah, anyway, COVID is not affecting so much. This is a natural growth and it will go on. European Union will use 10% energy from marine sources by 2035. Ocean covers 75% of Earth's surface and it is storing lots of energy. So if we harvest little bit also, it will be very good for us. And for India, we have 7,500-kilometer coastline. So that long coastline is having lots of energy. Long coastline is from coast some distance around 200 kilometers also you can explore. That is, I think Indian people can, Indian government can explore. So the energy in the form of say tide, wave, current, Salinity gradient, or many other forms. Like so wind turbine also you can install. We can install solar panels on the ocean, and we can harvest energy. Only wave energy itself can give energy needed in the world. Then why are you thinking future is green? It's not so easy task. So the answer will be there in my presentation. India is importing 75% of oil, and it is the very, maximum of foreign currency we are giving to other country, especially Middle East, Saudi Arabia, and other countries to buy this oil. If you can reduce this oil dependency, or if you can produce our own oil, or we can avoid oil consumption, then it will be good for India. So our development will be much faster actually. But there's no presently option is very limited. We have to import oil because renewable energy is still expensive. Maybe solar, wind, or any other form, still it is expensive. So why ocean? Ocean is the largest solar collector. So I already told the 70% of the Earth's surface is covered by ocean. So that is absorbing solar energy. And solar energy, when it is absorbing, so the air nearby the ocean surface will be heated up and it will move up. And because of temperature difference in different area on the surface, the wind will be blowing. So when wind is blowing from one point to another point, so that will fetch water surface from one point to another point. So that will create wave actually. So wave is created because of wind blowing over the ocean, and wind is coming because of solar action. So finally, energy is coming from Surya Dev. Electricity can be generated by change in salinity, thermal gradient, tidal level change, or ocean currents, ocean waves. No number of ocean energy concepts, more than hundreds, thousands concepts are available. I was doing some literature survey or patent search on ocean wave energy only. I got more than 1,500 patents on ocean wave energy only. And if I include tidal energies and tidal energy plus ocean thermal energy conversion plus other form of energy, then maybe several thousand of concepts will be there, new ideas. Many are already tested, many are in the concept stage, and many already implemented, failed. Ocean resources potential, present electricity production worldwide, even more. Okay, so whatever requirement is there in the world for energy requirement, ocean can give all the energy actually. So ocean was there in the past. If you see, lots of cities are located around the ocean coast, and ports are there. So lots of countries were dependent on ocean resources, maybe fish or transportation. And new era is that ocean energy we can explore. So now question is that, okay, fine. Why do you not see marine systems all around the coastline? This India, I told 7,500 kilometer coastline, but no one has seen any ocean energy system there. But why is there no such device supplying power to our grids? Let's say you are staying in UP or northern India. Can you get ocean energy through grid? Is there any commercial marine energy system? Can you give some example of successful marine energy system? So all answers I'll try to give through this next slides. So marine energy, see, mainly there are four types: wave energy, current energy, thermal energy, tidal energy. And another can be there called salinity gradient energy. River water. River water is having low density, and ocean water having lots of salt, so it is high density. So if there is any density difference, and if you put one membrane and put some mechanism, so that because of density difference, water column level will be going up, and use that water column to run turbine. So that salinity in India, no one has tried actually, but America and other countries, they are trying to get energy from the ocean density gradient, the salinity gradient. And some other form of energy are there, wind and solar. Wind energy, offshore wind turbine. If you see Germany and other Nordic countries, they're installing lots of wind turbine, offshore wind turbines. And I'm not including those as a marine energy because those are installed on the ocean, but not taking energy from the water. And solar energy, solar plant, like say solar cells also, you can put on the ocean surface and you can get energy. So again, I am not including into the marine energy list. So now marine energy, mainly 4 or 5 types. Now in these slides, I will try to discuss only wave energy, because if I have to discuss all these things, it will be very much haphazard. So let's focus on only one aspect, wave energy. Wave energy also, there are several concepts I already told, like 1500 and more concepts. So few concepts are there: point absorber, attenuator, oscillating wave surge converter, overtopping device, Archimedes wave swing, oscillating water column. So among all these, I'll discuss oscillating water column. Okay, now clear. Marine energy, among renewable energy, marine energy is one concept, and among marine energy, wave energy one concept. Among that, wave energy having many different designs. Among these designs, oscillating water column is one design. Now next, we'll go next. So some statistics, statistical data published some time back, International Energy Agency, 2006, and they have shown lots of energy is there, like ocean thermal energy. Thermal energy is written there. Tidal energy 0.3 K terawatt per year, tidal current, ocean wave, salinity gradient, thermal energy is ocean thermal gradient. How do you get the thermal energy? Thermal energy not like steam power plant or anything. It is ocean thermal energy. How do you get ocean thermal energy? Like when you reduce temperature of water, so water get denser. So dense water will be nearby sea bottom. But hot water, the sunlight heats up the surface water. So surface water will be low density water, it will be on the surface, but cold water will be at the bottom of the sea. So now surface temperature will be around 30 degree and bottom temperature will be 4 degree, because 4 degree centigrade temperature, water is having highest density. Okay, so now I have 4 degree minus 30 degree, it's 24 degree difference. So in 24 degree difference, this temperature, if I can use properly and to run turbine and compressor and other systems and make a like thermal power system, so we can get energy actually. So India actually already tried this one, OTEC system, they say, ocean energy conversion system. In India, they are running around 18 degree temperature difference, and they have already installed the system in Kavaratti and Lakshadweep area. They are producing desalinated water there, because Lakshadweep and Kavaratti, those isolated islands, Indian islands, those are not connected by grid because they're very far away from the Indian mainland. So you cannot give a big power plant. And some island population will be like say few hundred, 1,000, 2,000. So you cannot put a big power plant there. So only one option you have, you transfer oil or coal or any polluting fuel source and give them energy, because they are our people, so we have to give them energy. Or you generate local you generate power from local source. Local source means ocean is available already. So I told already there is lots of energy. Solar sunlight is available. So they can give that. So ocean thermal energy system in IoT, National Institute of Ocean Technology, Institute of Earth Sciences Laboratory, is located in Chennai. They are putting systems in Lakshadweep and other areas. Even Andaman also, I think they're trying. But tidal, I did one project with UK Queen Mary University, Indo-UK project, UK project. So we found that Minicoy Island, a small island, is there nearby Kerala coast, under Lakshadweep group of islands. So the fluid velocity is good enough to produce power. But question is that many questions are there. For example, this is Coral Island, so you cannot harm the coral reefs, and how to install, how much cost, lots of things are there. But our main target was to produce some to show that the potential is there or not. So we have proven that, and we have reported some articles also on that. And salinity gradient, I already told, sea water density and river water density different. So if you can run some turbine using that difference, then it will be good for you. You can get some power. Okay. And wave energy, anyway, I'll discuss in details. So huge amount of power is there in the ocean, in these forms, and all systems are in the basic stage. Tidal energy that is already installed in many countries. For example, France, they have installed a big system in 1964, around 250 megawatt power they are producing. And recently, 2-3 years back, South Korea, Siwa Lake on tidal barrage they have produced, and that's the largest, world's largest, 256 megawatt power they're getting from tidal barrage. Distribution of wave power along Indian coastline. So I already told that wave power plant wave energy we can produce, and potential is there 40 to 50 gigawatt power we can get. And this information is given in Ministry of Renewable Energy website. When our professors from Sundar and Professor Israel, they also produced one report for ministry, and they have shown 40 to 50 gigawatt power we can get from this wave only from the Indian coast. And where we can get power, you see the red zones. Red zones are having higher potential. These red zones, okay. These red zones are having higher potential. The blue zones are very low, almost zero potential is there. West Bengal area, this Andhra area, very low. But West Coast, if you see, much better. Chennai area where we are located, IIT Madras, so it is having also very low power potential. So red zone, like the southern part red zone, this Kerala area, they are actually India first installed their wave energy plant. Other area is there near Maharashtra and Maharashtra area and Karnataka area. There are options for wave energy harvesting. And this 40 gigawatt, what does it mean for that? I mean, this implies a few states, actually, India's few states power can be provided from this wave energy only. This is Tamil Nadu wave energy, we can give only from wave energy, but there are some issues I discuss. I have to close this annotation. Yeah. So I'm talking about wave. So how this wave is coming from? Wave is coming from sunlight. Sunlight is creating temperature difference between 2 points. Then one area air will be getting heated up, another will be colder. So colder means high density air, low density air. So low density air will go up, high density air will move. So this way air will be blowing over the ocean surface, and when air is blowing over ocean surface, this will move. The wave will be created. Yeah. Now, if you see, first you have to know the definition. Wave crest means this highest point. If you go to ocean area anywhere in Chennai or Mumbai or Goa, and then you see this wave is moving like this. Okay, it is coming to shoreline. So the peak area is called wave crest. The bottom area is called trough, and crest and trough, the difference is called wave height. And if you see the ocean, the wave is not smoothly like what I was shown here, sinusoidal smooth profile. It's not like that. It is not like that actually. Actually, it will be like this. Lots of peaks and valleys. So when we calculate wave energy, we do not take the extreme peaks or extreme valleys, because this will not give any power. So we use the term called significant wave height. So almost average wave height we calculate, and we try to get how much power is there in the ocean, in the wave. And whatever wave you see near the ocean, near the coastline, when you go to Goa or any other cities, that is actually breaking wave that is having lots of energy. But normally we do not use that one. We go a little bit deeper and try to get the energy. Okay, so I told that there are several types of wave energy systems are there. This OWC, a pico power is there. Okay, yeah. So OWC system is there. The pico power is there. Pelamis power is there. AWC, Archimedes wave swing is there. And when we are getting power from ocean wave, it is having this is coming from ocean wave. One air chamber will be there. I'll explain details in this thing. Where turbine will be there. Some controller or electronic mechanism, induction generator. So generator mechanism will be there. The power electrons will be there controlling power. Then it will be connected to grid, or it will be used for any for the purpose. So similarly, the other systems also will have so many mechanisms. So every mechanism has their own complexity. So that's why it is not becoming so much popular energy device. Other systems also similar deficiency or weaknesses are there. But still, we are doing research. Lots of people are investing money. Governments are investing money. Why? Why there is hope? So we'll discuss. Yeah. Yeah. So if you see this one, different paths from wave to energy. So this is wave we are assuming, and wave to if I see oscillating water column, what India tried, or I'm working for that. So first you'll go to air chamber, then some turbine, then turbine to generator, generator electronics, generator grid. So this is the path, flow path. There are other designs also available. For example, up and down wave, up and down motion is there, because we have seen like this. So if you see crest and trough, the difference is continuously changing. Okay. So when continuously changing, we can put some pistons, like say balloon, and one piston cylinder arrangement such a way that piston you pump fluid. So the first one you make like this: you pump fluid, you store the fluid, run a motor or turbine, then you get electricity power. Another is directly you store an accumulator, run turbine, and go to the generator and get power. Another is direct mechanical energy harvesting system. You have vertical motion of wave, and you put a rack and one pinion. While rack is moving up and down, pinion will be rotating. So actually, I have made one system. I'll not show here because this will be off the topic. So in that case, what I am doing, I put some gear, and the rack is there. So when it is moving, gear is rotating. So gear is connected to my generator, and I'm getting power. So this is the load for my another system. And another system, direct electrical drive system. So direct electrical drive system, you have seen the motor. I think you have studied, everyone has studied electrical engineering first year or second year course. So in that case, motor mechanism you have seen, coil and magnet will be there. If you fix coil is there. If you move magnet up and down, so there will be EMF generated in the coil. Okay. So in that case, what they are doing, so put coil layer by layer, 1, 2, 3, 4, 5, 6, 7, and move magnet up and down. So magnet will be connected to the wave. Okay, when magnet is moving up and down, and coils are there around, so coil will get EMF. So that EMF or electricity, you can collect and you can produce electricity. So that is called linear generator based electricity generator. So instead of rotary generator, you are creating a linear generator, and you are producing power. So everyone is trying their own way. So first I'll gear or drawing. I'll go to next slide. Yeah. So wave energy. Yeah, so wave energy oscillating water column, I already told that I'll discuss details. Wave energy, this oscillating water column, the plant in India, it was tried, and many other countries also tried. For example, Spain, Mutrico wave energy plant is there. You see in the picture, you can see. In UK also they tried, and many other countries also tried. South Korea, China, and many other countries tried. But many tried, many failed, and many still going on. Many new fund coming up. So many questions are there. So I'll try to resolve one by one. So I said that in India, if you can remember my previous one slide where I was showing, I will, yeah, I was showing that red zone is here for higher wave height and period. So some area higher wave height and period is there. That means wave is moving very high rate, and wave is having more energy. Water is very much calm, like ripple is going on, like in pond. You see air is blowing over it, and you are getting ripple. That means it is very low amount of energy, wave energy. So you can harvest it. But wave is very high, up and down. So in that case, actually you harvest energy. Okay. So in this area, it was red zone. So wave height is very high. Actually, Kanyakumari, this area, wave height around 2.5 meter we can get. But Chennai area half meter wave height. So 2.5 meter this area wave height, this we can harvest energy. But Chennai area we can harvest, but that will not be economical. Okay. So in India, this area, one area called VIZHINJAM, this Malayalam name. So they installed one system called oscillating water column in 1990s. And the story of this wave energy plant started from our department actually. Our senior professor, Professor Ravinder, and many other senior professors, they thought, okay, in lots of wave energy potential is there all around India and coast. So can you install something? Then they started doing research from 1980s, 1983. Then finally it got installed in 1990s, I think 1999 or sometime. And initially it was giving some power, but it's not so much high. Okay, so finally they dismantled actually. So I'll discuss later what are the reason, many other. Then after that, NIIT got formed. NIIT National Institute of Ocean Technology. This means Step Sciences Laboratory in Chennai. And the NIIT. So initially it took birth from a department. So our department professors become director of the NIIT because then NIIT got new space. So initially started from our department of Ocean Engineering IIT Madras. NIIT got their space. Our professor become director there. Then NIIT and IIT Madras jointly they are doing research, and still IIT Madras and IIT cell is there. So normally we do projects jointly together, which are having real application. Uh, yeah. So then after dismantling, NIIT tried to develop another system called floating wave energy system. So this is NIIT marking is there actually. You may not be able to see. So they developed in 2000. Yeah, after dismantling this one, after dismantling this main one, they developed this floating one. This. Yeah. So if you see this picture, I took from one book written by Professor Jaishankar and others. It is published by NIOT itself. Okay, wave energy during construction, you see this big system. So people are standing and they're constructing. And so this is the picture. This wave energy system. The turbine will be located here. I'll explain details later. Okay. How much vapor is there in wave system? So there is a formula we use normally for calculating how much power is there. Vapor per in wave front, J equals alpha H square T. H means wave height and T means time period. If time period is very high, so we can get more power. Wave height is very high, we can get more power. Wavelength calculation. So we use this formula. So maximum absorber power equals L by 2 pi by J. L, I think this is wavelength. Now we'll go to wave energy oscillating water column. So till these slides, you have seen oscillating water column and wave energy systems. Now I'm trying to focus more on oscillating water. What is the system? How does it work? Okay, so first see the video and the picture. annotate. Okay. So in this picture, first you see the picture, instant wave is coming. Instant wave is coming, and this is one structure. So wave, water will push this one, and this area air. So this is simple box, and air will be moving out this one if wave is entering. Wave is pushing water here, so air will be pushed out here, and when wave is going down, so water will be entering like this. So like we are breathing. Okay, so wave is pushing like we have in stomach, we have diaphragm. We are pushing diaphragm. Air is going out. When diaphragm is going down, so it is doing like this. So this will be breathing continuously, inhaling or exhaling when wave is coming and going. Okay, and on the way there will be turbine. So this turbine will be rotating continuously. This is special type of turbine, not a common turbine. So I'll explain what is the special turbine. And this is by near this is near post one structure. So this is called fixed structure. So now you see the video. I'll explain. This same thing in video also. This is a path of air. Air is going out through this. Okay, wave is coming. So air water level moving up and down continuously. Here you see this water level going down, up. So air is going out. Air is going out. Again water is going in. So continuously air going in, out, in and out, in and out. So breathing, it is breathing, and turbine is located here. So turbine will be rotating. So the turbine will be rotating, and you will get power. So this video was generated by Python company. Yeah, so I told you that there are several types of wave energy system. One is fixed type, another is floating type. The NIIT both tried actually. Another is there is this one, another very small type wave energy system. There is one turbine. There is one turbine. There is one turbine. So previous video you have seen like this: wave will come, water will come, and it will go out. And again, air will enter here. So continuously breathing will take place. Here also breathing will take place here like this. The small system, spark buoy type system. This is another system. Yeah. So in IoT and IIT Madras, both were involved in these designs. Read first. Is we yeah. Yeah. So I already told that OWC uses turbines. So we say air turbine. So you have seen oscillating water pump system. Water is going up and down, but water is not running turbine. Rather, air is running the turbine. Okay. I cannot do that. Okay. So actually, the turbine is running in the air. So there are different types of turbines are there. One is reaction turbine, another is impulse turbine. So NIOT or Indian authority, they use both type of turbine. So I'll not focus so many things. I'll focus only one or two aspects. So reaction turbine. So reaction turbine or Wells turbine also, it is having guide vane without guide vane, with guide vane, selfish control, biplane, counter-rotating, many types of turbine. So I'll be focusing basically without guide vane Wells turbine, a simple turbine. And some other turbine also I'll show. So we have done CFD and numerical work. And why did you do this one? So I'll explain that also. And impulse turbine, if you see, there are several types of impulse turbine, so I'm not focusing on that now. Okay, so OWC, oscillating water column, and turbine I say, but why this turbine research or IIT Madras is doing from 30-40 years? This is what is the significance? Of whole world is working on many aspects or many areas of turbine and OWC design. But what is the problem? If you see this picture, you will understand something. So energy in the wave. So if we have significant wave height and we calculate, say, assume 100 watt power is there in the wave, and how much power we can get? Air chamber. So when wave is coming in and out in the air chamber, so there will be losses. So you'll get 75 watt. Say 25% loss will be there, approximate thumb rule. Then air turbine. So then air will be running a turbine. So air turbine will have 40% or lower performance efficiency, or it will give 40% power or less. So well turbine is having higher power, impulse is having lower power, but they are having their merits and demerits. I'll explain later. So air turbine is the major loss will occur in the air turbine only. Then there will be generator loss and control and other losses. So assuming unidirectional airflow and air is it is an ideal condition. So wave is completely sinusoidal. There is no ripples or any other thing. Okay, and why what unidirectional bidirectional, that explanation I'll give later. So finally 100 watt it become less than 25 watt. So sometime I argue that if you give me 15% power from OWC system, I'll be happy, because there are so many other losses also I am not including. I am giving the major loss where you can get. Okay, so say maximum 20% power you'll get. More than that, if you want to do, then you have to do more research. So let's see the next. So conclusion up to this level, energy potential is there. Wave is having lots of energy. You got it. Some systems are installed already. Low power output and uncertainties are there. That's why many Indian wave energy plant got dismantled. Many other also got dismantled. Then what is the next? Why we are doing research? Then where is the catch? So we'll go to the next 25 slides. Okay. So now we are focusing more on Wells turbine. So Wells turbine, if you see, it is having symmetric blade. I'll explain. Yeah. So because this is COVID time, office is locked, so I cannot bring my original turbine. So I made using paper some turbine. I'll show you how does it work. Well, turbine it is having symmetric blade. Symmetric blade, if you see this picture, annotate.
Yes, sir. Yes, sir. It is visible, sir.
Clear?
Yes, sir.
Okay. Yeah. Okay. So this is symmetric blade is there. So here also, if you see this one symmetric blade, actually, I created in the paper. So don't calculate this one Naka blade or which blade. This is a symmetric. This area and this area will be symmetric. Okay. So this is having 4 blades and it may have 6 or 8 blades. So normally it will have 6 to 8 blades. Okay, because I'm making from paper, so I made only 4 blades. And when air flows from the top or from bottom, air flows from this one or opposite direction. So turbine rotation will be unique. This is leading edge, this is trailing edge. So turbine will be rotating in leading edge direction, right? So if you see this one, this is small thread. I think you cannot see this. I connected. I tied this thread so that you can understand how it is rotating. Okay, because here, if moving from the top, it will be rotating in this direction. If moving from the bottom, again it will be rotating same direction. You see, I'm moving it vertically up and down, and it is rotating in one direction. Is it clear? Okay, can you see? Anyone can confirm? Yeah. Okay.
Yes, sir. Yes, sir. Visible.
Yeah. Okay. So this is leading edge. So it will be rotating continuously in one direction. This is called bidirectional flow, but turbine rotating in one direction. Flow is bidirectional. So if I fix the turbine in one place and my airflow changes direction, like in picture, if you see in slide, the red dot I have put, and I have put animation. Red dot means air particle moving up and down, but turbine rotation will be in one direction only. It cannot rotate like this. Okay, it must be rotating in one direction. So one direction rotation benefit is that if it is connected with turbine shaft will get unidirectional motion, and it will be connected to generator. Generator will be producing power constantly, continuously. Okay, but if you do not do this one, if you use normal turbine, then it will be rotating in one direction, opposite direction, one direction, opposite direction. So that will not work in this case. Okay. So symmetric blade is there, faces bidirectional airflow. So turbine called bidirectional turbine, rotates in one direction. And if I have cambered airfoil like this in slide, if you see, so the turbine will be rotating clockwise and anti-clockwise. So we don't need that one. Okay, here on drawing. Yeah, so the same thing, force calculation formula is there, L sin alpha d cos alpha. So although flow direction changing, if you see in the picture, okay, yeah, you see this flow direction here and flow direction here, flow direction changing, but turbine will be rotating Ft, tangential force is same direction. The turbine will be rotating the same direction. Okay. Here all drawing. Okay. Now, why bidirectional flow turbine? Bidirectional flow turbine I already explained. If flow direction changing, turbine cannot rotate in both direction, clockwise and clockwise, so we cannot use this one. So waves moves up and down. Turbine is having rotational motion. The shaft assembly is the only moving part. Motion is harsh. Motion is harsh means if you have many moving parts, actually this system will fail quickly. So increasing relative moving part in system makes it unreliable. So any system you design, if you have lots of moving part, system will be unreliable. That's why like aircraft engine you have gas turbines, so only one shaft rotating system. So it will be more reliable. So similarly, ocean wave energy also, so many uncertain things are there. If we have more moving parts, it will be more uncertain and life will be difficult. The shaft assembly is only moving part, and another is that wave moves. Yeah, so wave moves up and down, and it is giving like breathing action. We are taking breaths. So continuously flow is reversing, but turbine must be rotating in one direction. That is the main mission. That's why we use bidirectional turbine. Now we'll be going inside the turbine now. Okay, now we see the from renewable energy, marine energy, wave energy, oscillating water column, turbine, Wells turbine. Now, within Wells turbine, we are moving into the further details. So Wells turbine, if you want to design, modify means why should you modify? Wells turbine, if you want to modify, then issue is that we have to increase efficiency of torque, and we have to increase operating range also. And why operating range higher is required, I'll explain later. So we have to, our main objective of this research of Wells turbine design optimization is that to increase efficiency or torque and operating range. I'll discuss details later. First, you see the different parameters, which parameter we can change so that we can change the objective functions. So tip groove height width, aspect ratio, number of blade, rotational speed, inlet condition we can change, generator characteristic change, tip clearance, sweep angle, many parameters we can change. So performance indicator, power output, efficiency, pressure drop, flow rate, operating range. So these are many parameters are there. We can modify and we can get different design of turbines. So this is not one day job or one student job. This is there. If you ask me, I can create 1,000 turbine parameters. It does not. And this is true for all types of turbine. Like say you take gas turbine, steam turbine, or any other turbine, you can create more than 1,000 parameters to design a turbine actually. But major turbine parameter normally we take and we try to change efficiency, performance, other parameter. Because I was my PhD is on gas turbine blade shape optimization actually. So I also changed several parameters there. Again, here also I'm changing parameter. Still, there are too many parameters or too many things are there in turbine systems. That's why this gas turbine people, especially gas turbine and steam turbine, those people, they are doing research. Still, people are doing research to improve performance. So many things are there. Okay. Now, actually, I have shown you in one slide that there are basically two types of turbine: reaction turbine and impulse turbine. Reaction turbine or Wells turbine. So Wells turbine, impulse turbine difference there. Wells turbine is having very high efficiency. Annotate. Yeah, so very high efficiency. Wells turbine is having very high efficiency. Okay, but impulse turbine having lower efficiency, around less than 40%. See here, but Wells turbine is having 60 or 67%. But issue is that it's operating range. So Wells turbine, like wave height when increasing or decreasing. If you see sinusoidal, means when wave is increasing, so at certain time wave velocity is 0, increasing again 0, then increasing 0. So wave is giving zero, increasing zero, increase. So it is not continuous flow system. It is varying flow system. So zero highest velocity, zero highest velocity is doing like this. That means our turbine will run only for certain velocity range. If you have very low velocity, turbine will not extract power from the wave. If it is very high velocity, turbine will not be able to extract power because there will be flow separation. I'll explain flow separation later. So this operating range is very low for Wells turbine. Okay, so when operating range is low, it will give lower power. But impulse turbine is having lower efficiency, but is having larger operating range. So sometimes people prefer this one because we need larger, large amount of air should give power. Sometimes people say, okay, take maximum efficiency or maximum power possible, then discard the small velocity or very high velocity areas. Okay, so I'll not go to debate for this one now. I'll focus only on Wells turbine now. Yeah, so Wells turbine, there are several plants installed: Limpet, Pico, Mighty Bell, Energy Tech, Mutrico. Many plants were installed with Wells turbine. Even Indian plants also they installed. They tested with Wells turbine. Okay, so the Wells turbine, there is hundreds of parameters can be created to optimize to this performance. And on performance, and in our work in our IIT Madras, we have done some work like casing groups, stall fans, pipeline turbine, and some experiment. Some other tasks also we have done, but I cannot show everything here because we have time limitation. So I'll show few of this. Okay, so okay, so one thing I have to explain here: Indian wave energy plant dismantled because the low power output. It was giving power, but power output was very low, so they dismantled. But they had to look into the details of turbine. This turbine was the weakest part, so I proposed that one, and I got project, and I did their work for them. So let's go to the specific topic, casing group, how we are getting higher operating range and power. Because I said higher operating range is very important for me, or high power is important for me. So then to do this one, we can change any parameter like sweep, lean, casing, or many other parameters. So first, we did a work called casing group, and we published in Energy in 2016. There we have turbine we have casing. So casing, if you can create one roof, then the turbine leakage flow will be changed. So whenever you read any turbine paper, then tip leakage thing will be mentioned. Tip leakage thing means when turbine is rotating, some fluid will be leaking from high pressure to low pressure area. When fluid is leaking, so this low pressure fluid will create another vortex here. So main vortex plus this vortex will create flow separation further. So that is not desirable for a turbine. So people are trying to reduce how can reduce the flow leakage so that it will not interact with passage vortex and will not increase my flow separation. So what they do, they put some groove, sometimes they put some end plate so that the leakage can be reduced. In some cases, they put some slot and sucking the low pressure fluids, or many other techniques they use. So Wells turbine also, we created one specific type of grooving, and that groove increased our performance. And we reported in very good energy journal, there's effect factor more than 5, I think. So why casing groove? If you see this picture, okay, what is not coming? Sometime annotation going hiding. Yeah, got it. Yeah, so these when fluid is passing through this gap, is called passage vortex. Okay, it's going like this and passage vortex, and something leaking from here. You see this from tape is leaking, high pressure to low pressure. So the leakage is interacting with this one. So this will create flow separation. Flow separation is that, like if you see this airfoil and fluid is moving this one, and there is lots of things are there. Fluid is not getting to be attached. Something, yeah. Okay, so fluid is not going to be attached here. So this detachment or separation is a problem for any turbine or aircraft engine. For example, if you can remember this Indonesian air crash few months back, I think more than 1 year back, they got crashed. This one actually my son's aircraft. So what happens when aircraft is taking off? So it is making certain angle. If angle is more, so there will be flow separation more. If flow separation is not controlled, then it will not get further lift. Rather, it will fall down or it will have some haphazard something. So in turbine also that's happening. So if you have lift, improper lift or fluid velocity changing, let's say you are changing fluid velocity laminate to turbulence quickly and fluid velocity is very high. In that case, again, flow separation will be there. If flow separation is not controlled, then the aircraft cannot get lift. So similar phenomena occurs in turbines also. So in turbine, if we cannot control the flow separation, we cannot get proper lift or energy or power. So we have to control this lift. So that's why the mechanism tip grooving we introduced. Okay, so after introducing tip groove, we did lots of CFD simulation. We got this CFD results. And relative torque coefficient improved by 33% from our research. We got relative stall margin. Stall margin is like which range we can run the turbine. Like x-axis was flow coefficient, y-axis was efficiency. Our range increased by 18%. Okay, so we change only groove. With groove, if we mix other parameters, sweep or lean and other parameter, maybe it will improve further. But it was one PhD student's work. This huge task were there, and some other student added some more things. I cannot show everything. The slides show limited portion. Okay, so we did some unsteady flow simulation also. Wave energy system. I said that this is sinusoidal flow. Sinusoidal flow means if you do simulation in any commercial software like ANSYS or OpenFOAM, you have to give input velocity. You can give fixed velocity or you can give sinusoidal input. Our case, sinusoidal case. So we gave sinusoidal input. And finally, we got this result. In this result, what you can see, we gave this much of velocity, but we got result this one, torque, force. Force means initial when turbine air is having lower energy or lower velocity, so we got lower torque. That's fine. But when torque increased, air velocity very high, so we got very low torque. So forget about this negative positive. Just see the magnitude. So we got very low torque. Why? Because flow separation occurred. Okay, so Indonesian aircraft, they plunged because this flow separation occurred and they got very low lift. Torque is lift actually. So then they plunged into ocean. So here also in turbine case, we got this much of this phenomena from our study simulation. So if we can reduce this area, this flow separation area, or if we can increase this one, this smaller area, this both cases we can get better turbine and better power from ocean. Now optimization. Now from OWC turbine to some tip groove system we discussed. Now I'll show some optimization, how we do optimize. Like so, initially we got the idea of grooving tip. Now we don't know what is the size of the tip, the height and thickness or weight. Many parameters are there. So that one we have to get through optimization. So for optimization, what I do? I go through surrogate based optimization model. So that code I developed 10 years back in PhD actually. So what initially I do design of experiment, numerical analysis, any CFX, Fluent or any other software I use, low fidelity model I use, surrogate, then optimize, then I get optimal design. So from that I can say, okay, this is the better design than previous one, so we accept this one. Okay, so for sampling method we use the different sampling technique, and one example is that we use two parameter for optimization. One is RPM or turbine rotational speed, and V velocity of turbine velocity or rotational speed of the air velocity from the OWC. So from that we create this response surface of 3D surface. So from 3D surface, we can get optimal design. Okay. Now we have done lots of CFD, numerical optimization. Now same thing, we have done experiment also. But and this picture, whatever you can see on the screen, is actually wave energy system, or sorry, bus turbine for wave energy system. NIOT used for their system. Okay. So to go to the laboratory, first I have to tell some story actually. I joined in 2010. I joined IIT Madras in 2010. Then I was roaming around in our laboratory, that big wave basin area. Then I saw some glass structure, and I asked one lab staff, "What is this?" And they said, "Sir, this is wave energy system. IIT Madras initially developed, and NIOT developed actual full-fledged model." Then something triggered in my mind, and I thought, okay, let's try to do some research and search some article and see what is the case actually, why this model is there, why. I want to know. Then that started my story of doing wave energy research, and finally I installed a big laboratory. I'll show later, and I got projects also. I got involved with an IoT real life project. Let's see the experiment system. So initially I got laboratory space, and this was developed. You see this one. So big machinery I installed. This is creating wave actually. Forward backward motion is simulating wave. Okay. So this is a long pipe, and turbine is here. Green area, blue area, the turbine is here. Okay. So this, if you have seen this forward backward motion of this system. So forward backward, that is mimicking wave. Wave is pushing air, and inside air is there, and through the duct air is passing through the turbine. This blue area is turbine area. So inside the this turbine, I cannot show here because my system is not transparent here. All are acrylic here. So this blue area here you can see. Blue area is the turbine area. You can see pressure tapping is there, piston chamber arrangement, motor is there, a big motor. So whole thing we have done from zero actually. There was no lab space and done. This is also again a graphical presentation of picture, our laboratory system, and this wave energy system turbine. You can see here. There is annotation. Annotation is hiding something. Yeah, now you got annotation. Yeah. So we designed initially using 3D printing. Okay. Now we got this broken because it was very weak. Our power was very high and it was very weak, so we got broken. And this is blade also got broken. So initial one student, Tapas Das, he made all these things. He's this student. Then he got broken. Sir, we got broken. What should I do? Then again, we found some other money to make another system. So this annotated system. Use this notation. Yeah. So then we created biplane turbine. Biplane turbine is initially we got this monoplane turbine, and then this picture you can see there's two plane. One row, another row is there, and same hub is there. So we designed and we put in between some guide plane also. This is guide plane. Guide plane also we put in between this plane. And we did lots of CFD and experimental work also. We reported in Journal of Fluid Engineering and Journal of Energy also. So I'll clear now, clear all drawings. Okay. Now, stall fans also, like in many aircrafts, you can see there will be some ribs all over blades so that you can separate, you can break this vortexes, big vortexes. So that also we put on the surface and we reported. And then after that we did experiment. Experiment when we did inhaling and exhaling situation, like we have turbine and flow is moving like this, forward and backward, inhaling, exhaling. in that case, we got different figures, CT or stroke length 4 seconds, 6 seconds, and we have drawn this picture. Now, think, audience, you can think this one. You have lots of pollution. You have this pollution. Now you have to make world like this, like this. Thank you very much. And all the work were reported in many newspapers and Doordarshan, Chennai Radio, All India Radio, Invention Intelligence also. And thank you very much. And you can ask questions or whatever.
Thank you, Professor Samad.
Yeah.
Thank you very much for nice session, very nice session.
Yeah.
So there are some questions.
Yeah.
I will request the participants to raise their hand if they have a question. Always Guljar. There is one question from Always
Yeah.
Guljar. I
Yeah, so
will.
where is the
I
range
will unmute
question?
him.
Now, where can I see the range question thing?
I will unmute him. Yeah,
Yeah, okay.
he will ask the questions.
Okay.
Mr. Guljar, you can unmute yourself. You can ask the question.
Good afternoon, everybody.
Yeah.
Assalamu alaikum, Professor Samad.
Yeah.
Sir, I am assistant professor at presently working at Islamic University of Science and Technology, J&K.
Okay.
I have three simple questions. First thing is, do we have any commercialized projects working anywhere in India? First question. My second question is, what can be the prospective research areas in this area? And third, what can be the entrepreneurial areas that beginning entrepreneurs can work for in this upcoming area? Thank you.
Yeah, so in India, there's no commercial system now. Only NIIT developed one system that is also came in news. I think the Doordarshan, if you see there, I think I have spoken there. Called navigational point. Ocean, if you go to ocean and a ship, yeah, first see the traffic. Traffic lights are there on the street, and that will guide you when you're driving bikes or anything. Okay, so in ocean also they need some guidance, something like that. So they call navigational point. So navigation point is some power, let's say lighting or any other source if you have to give, then that power will come from ocean wave. So NIOT has developed a small wave energy system, and I designed turbine for them, and that is the only system in India there. And some other concepts people are here and there small trying, but no one is successful yet. Even all over the world, everyone is trying. And everyone is trying to generate new ideas. For example, one idea we are trying, wave energy based desalination system. Last summer in Chennai, we had no water almost. I mean, in IIT campus also, we got very, water supply was reduced to 1/3. Okay, because of water shortage in Chennai. Although we have ocean. So wave energy can give power. So that one we are doing one project with the Department of Energy of the United States. Let's see, several concepts are coming up, and entrepreneurship if you want to do, then you have to bring a new idea. Like one eco power is there in Israel company, so they are trying to install lots of wave energy system all over the world. So people are trying in this way, and in India, actually, we are trying IIT Madras and NIOT. They are trying. Others are not visible.
How long we can see that this technology can be commercialized in coming years? How many years we can say from now?
Commercialize, say at least 10 years.
10 years from now.
They say I'm trying with something with DRDO and Ministry of Defense. They say offshore sensors and other thing if we require, then maybe we can give power from ocean wave. The small power required, and maybe 500 kilometer from mainland. So a small power source if you can generate from ocean wave or something, that would be very helpful actually. So that one I'm discussing with ministry. Still not finalized, but we are discussing.
Thank you, sir. So nice of you. I must say that there are a lot of opportunities for the young researchers and beginners who just want to work in this world, in this area.
Yeah. Yeah. Okay. Thank you. Thank you.
Thank you.
Professor Faiz, next question is from Professor Faizan. He has raised the hand. So, Professor Faizan, you can unmute yourself. Professor Faizan, you can unmute yourself. Yes,
Hello,
you
sir.
can. You can ask question.
Hello. Yes. Hello. Can you listen me?
Yes, yes, you are audible.
Hello.
Yeah.
Yeah.
Yes, Professor
Sir,
Faizan, you are
actually,
audible.
I just asked. Yeah. Actually, I just asked that question. Okay, when we see that there is a marine wave, wave motion, can be can be affect day and night effect also take place in the consideration of the wave turbine system.
I did not get the point. Actually.
Hello.
Your
Actually,
voice
sir,
is
we
not
have
clear.
seen that the motion of the tides is affected by the moon also. No?
I
Yeah,
think
tight.
Hello.
I think he want to ask that whether some the effect of moon is there in
Okay.
the yeah.
Wave
I
system.
Yeah,
think so.
if is a day night effect also take considered for the efficiency of the for system. That's why I'm just asking.
Okay. Wave energy, when we are considering, we did not consider that tidal effect. Because we are trying to design system such a way that tidal, if water level rising or getting down, so automatically it will adjust itself. So we are not considering that tidal effect because already it is very complex system. If we consider tide also, it will be difficult. So wave and tide we do not couple. Okay, we try to avoid tidal part. Okay.
They are different things.
Thank you.
Yeah, two different things.
Okay.
They are two.
And one question is from Rakesh, Mr. Rakesh.
Okay.
Mr. Rakesh, you can unmute yourself.
Yes, sir.
Mhm.
Sir,
Now
first
you
of
can
all,
ask.
good morning, sir.
Good morning.
Sir, actually, I want to ask that what will happen if if the waves are stopped, and is there is any mechanism or for continuous generation or continuous movement of the blades?
Yeah, wave normally wave will not be stopping to zero. There will be some motion, but because of momentum, turbine and generator assembly like magnet is there. So because of momentum, it will continuously few seconds it will be rotating actually. It like wave is moving up and down. So in between there will be almost zero power sometimes zero power, but still it will be rotating because of this system momentum. Shaft and magnet and turbine whole system will have some momentum, so that will push for rotation. But Wells turbine
Okay,
is
sir.
having starting some problem, so many people are trying to solve that one also. Like at the beginning when you are installing and there is no wave, so starting will be some issue for Wells turbine, but impulse turbine is not having such issue.
Or sir, I want to ask another question. A little question is that what
Okay.
will be the effective material used for making turbine blades of that type of turbine which is used in a marine system and all?
Okay, marine material is very important part because ocean water is very much corrosive.
Yes, sir.
So if you put any iron sort of material, it will be corroded within few days. I mean, it will not take long
Okay,
time to
sir.
corrode.
Okay, sir.
In our case, we use like non-metal material like acrylic and the sort of material, and we test it because we are testing for shorter period of time. In IoT, they made for longer period of time. I think they made metal and with some coating.
Okay, sir. Thank you, sir.
Sir, another question is from Nikhil Dev Garg. Professor Nikhil Dev Garg, you can ask the question now.
Namaskar, sir.
Yeah,
Namaskar,
hi.
sir.
Yeah,
Sir, my question, I am having two questions, sir. First question is, whenever we are going modeling for the gas turbine, we are mostly changing the effect of temperature on the property of specific heat and other properties.
Okay.
But generally, I don't found much literature which is dealing with the effect of pressure on the specific heat. There may be some difference. Maybe I have not studied all the literature, or there is something. But I found that effect of temperature is being taken in many literature, but effect of pressure is not being taken. So why it is so, sir? It is my first question. And my second question is, sir, what is the difference between stalling and surging?
Okay. No, so first thing is that you are talking about gas turbine. You are talking about gas turbine or hello? Can you hear? Can you hear?
1 minute. I will again unmute himself. Professor
Just,
Nikhil, you can unmute yourself.
Yes, sir. I am talking about gas turbine, sir. Yes, sir.
oh, yeah. So because our turbine is very low pressure and low to normal temperature turbine, so we do not consider all these complex things.
Okay, sir.
Okay. And surging means back pressure if very high, then it's a surge. But in our case, back pressure is not so high because all low head turbine, like say 1 bar pressure will be normal, and maybe 1.5 bar will be maximum difference between inlet and outlet.
Okay, sir.
Okay. This is low head turbine.
Thank you. Okay.
Gas turbine is very high head turbine.
Okay, sir. Thank you, sir.
Sir, next question is from Professor Karimi. Professor Karimi, please, you can ask the question now. Professor Karimi, you can unmute yourself and ask the question.
Dr. Samad, very kind of you to deliver the lecture.
Okay, thank you.
I have two parts of my question. Number one is, what is the most recent area one can do a research on this particular topic? Is there any topic on which people can explore themselves?
Okay, so
And
actually from
do you
my
have any suggestions? Yeah.
Yeah, from last 10 years, my work and NIIT, all the stories now I know. So, like bigger wave energy system is not good. Smaller wave energy system for small power requirement, if you can design, that would be good actually. So, smaller power requirement, say offshore, any requirement, like say desalination of water, we are doing one project. Let's see what result we get. Or maybe a small electronic surveillance system required for offshore systems. So small power requirement is there. So that thing we can try. Big systems, big money and big failure, and that is very difficult to digest because India already tried and they got that failure actually.
About the research area, I was thinking.
Yeah, research area.
Research in Delhi. So is it?
Okay, so research area, for example, I'm focusing on small systems. That's why I'm talking about. Small system is the power requirement.
We can only do some CFD modeling. So I was thinking of some CFD modeling of this. Is it possible?
Okay, CFD modeling, let's say fluid structure interaction of this wave energy, floating wave energy system we have, how the fluid structure will interact. As a wave is moving and structure is moving, how it will resonate. If it is rolling very high, it is good for me. I will get more energy. But if it is not resonating properly, then it will not give you proper power. So if you can give me some data, like say, sir, you take this much of size for this much of wave height and period, then you'll get more resonance. Then it will be helpful for me. That is, it will be helpful for the designers. Because I am focusing more on design part.
Okay, one last part is that as far as my knowledge is concerned, I know there are different types of aerofoil which are already prototyped. So is there any particular prototype aerofoil which is necessary in case of tidal energy evaluations?
Yes, tidal energy my students are doing. I think we are taking 1 meter diameter, one turbine, and we have a Indo-Korea project, Indo-German project also. I think Indo-Korea project one. Yeah. Indo-Korea, the tidal energy, they have big tidal turbine system, and I got in DST Korea fund to design one turbine. And so, what type of profile they are using, I forgot. So I have to ask my student. So if you can send one email, then maybe I can ask my student what they're using. Because this whole national university, they have one tidal turbine testing and facility. So I'm working. We are jointly working with them. Okay.
Sir, there are so many questions, but we can take the only last question. Other questions can be taken on mail. Persons can mail you or mail to ourselves, and we can answer them. So there is, I think, one question from Professor Karna, Dr. Shyam Kumar Karna. If you are able to listen me, you can answer. You can give your question. What is your question, Dr. Karna? You can ask your question if you are able to hear me.
Yes, sir. Sir, you have talked about optimization technique for this OCW. So can we there optimize by applying Taguchi techniques?
I think anything can be applied, but whatever I have developed my own code, so I normally try to use that one.
But in Taguchi techniques, with more parameters, then experimental calculation becomes simple.
Okay. If someone can help me, it will be good for me.
Okay, sir. Okay, sir.
Yeah.
Thank you, sir. Thank you.
Yeah. Okay.
Thank you, sir. Thank you.
Yeah. Okay.
Professor Samad, it was a nice session, highly motivating to utilize the ocean energy to generate electricity. Uh, Now I will request Principal Sir to say a few words, vote of thanks to our expert speaker. Principal Sir. Principal Sir, you can unmute yourself. Sir, you can unmute yourself.
Hello, am I audible?
Yes, sir. Audible. Yes, sir.
Thank you, Professor Ahmad. It was enlightening. It was a wonderful presentation, and we would like to thank all the audience present for their active participation and queries. And I feel that it has opened a lot of avenues for future research also. Especially we in Delhi, as Professor Karimi was asking what we can do here. I feel, could you throw some light on micro and mini hydel projects, micro turbines, micro level turbines?
Yeah, actually, one of our colleague, Dr. Professor Dhiman Chatterjee, IIT Madras, he's working with IIT Roorkee, the renewable energy department is there. So they have already developed one small tidal turbine based system, or tidal turbine, low head turbine for Uttarakhand, some application. So if someone is having some specific, information they need, so then I can forward that email to Professor Chatterjee. He may think to reply, or they will get much better answer.
Right. Because we are not around the coastal area.
Okay. So yeah, Professor Chatterjee, maybe the person who was searching, they can check with Professor Dhiman Chatterjee profile. Even I can speak also if someone is in the question.
So, sir, thank you very, very much for your very wonderful presentation, and it was very enlightening. And hope we will continue our association. And if some of us visit your laboratory, we'll be keen to meet you.
Yeah. Okay. Thank you.
Thank you, sir.
Okay.
Thank you.
Yeah, thank you.
Thank you. Thank you, sir. Actually, I personally have a question, sir. If you can answer. You have shown that well turbines are more efficient than impulse turbine.
Okay.
So what is the probable reason for that?
The mechanism completely different actually. More efficient means only for shorter period of time, but on an average power, if we see, like shorter period of time, it will give very high power, but other time it is not giving power. But impulse turbine is giving average higher power. So this is matter of choice actually. European people, they choose West turbine, some other people choose impulse turbine. So that sort of things are happening. So in India also, in IIT and within South Indian plant, so they tried both actually. So both needs improvement, and my group is working.
What about tidal versus wave?
Tidal is having more power, but in India, what is happening in Gujarat area, Kambe basin area, and Kutch area, and West Bengal, Durga Dhwani, some area. So both cases, government studied in West Bengal abandoned the project because it's very expensive, and Gujarat area that government still studying, and it is expensive and it will take several years. One newspaper report was that it will take several years to install, but work is going on. I think work going on means study going on, not installation. So in India, it will take some more time for tidal, but it will give more power.
Okay, sir. Thank you. And for all of those present, tomorrow's session will also be very important. The advanced CFD. It will be taking the fluid solid interaction It will be
No,
very.
sir. Excuse me, sir. That will
Oh,
be on
sorry, sorry,
9th.
sorry. Okay, 9th. Right. Okay.
Tomorrow is the industry person, Mr. Naresh,
Okay.
and he will be delivering on the design blading aspects of steam turbine blades.
Okay. Hope to see you all tomorrow.